is so massive that finding ways to minimize the effects of wind is a vital element of its design. Engineers and scientists begin with the building's exterior. They find that by using re-entering or saw-toothed corners, the flow of wind around the building is drastically reduced.
The results of wind tunnel testing, the re-entering corners help to reduce the dynamic wind response by 30 to 40%.
Saw-toothed corners on a building hinder the formation and impact of the small wind vortexes that can cause it to sway. But just like the pumping of a child's legs on a swing, where each push adds energy to the last, even when the effective wind on a skyscraper is reduced, energy will continue to gather unless it's removed. It's not the size of the push that matters, it's the repetition. If engineers can find a way of cancelling this accumulation of energy, then the building's contradictory requirements of strength and flexibility will finally be met.
Usually, a lot of tall buildings use so-called computer-controlled mass to do that function. In our case, I think our very smart engineers come up with this passive tune mass damper.
The passive damper on 101 uses a huge weight hanging from an upper floor to counter the effective wind. As TAIPEI 101 sways in one direction, the tuned mass damper swings in the other, cancelling the buildup of energy and reducing the building's motion. Engineers of TAIPEI 101 have made the impossible possible, designing a building that is stiff enough to survive a typhoon, yet flexible enough to survive an earthquake. But although these ideas seem to work on paper, they are yet to be proven in practice. 101 is going to need a lot more than just new design to combat nature. It's going to need entirely new materials and construction methods as well. TAIPEI 101's unique megastructure and wind damper will make the building resist the impact of earthquakes and violent storms. But all of this engineering means nothing unless the giant building has a solid foundation on which to sit. Finding solid ground in Taipei is a lot harder than it sounds. Over hundreds of thousands of years, changing sea levels have filled the Taipei Basin with layers of soft, unstable silt and clay. In order for the tallest building in the world to remain standing, its foundations must penetrate through this layer, sometimes 60 meters thick, to find the solid bedrock below. Geotechnical engineers spend 8 months collecting core samples to analyze the soil on the building site. They find 3 distinct layers of soft sediment before finally reaching solid ground. This information helps designers to develop detailed plans for 101's foundation structure. Preparing the foundations takes 15 months and removes 700,000 tons of earth from the site. The foundation of a skyscraper is one of its most vital structural elements. It must distribute the building's enormous weight evenly below ground, at the same time creating a super strong base for the towering megastructure above.
That's the key point for the whole building, that the building can stand up into the sky.
To compensate for the inherently unstable ground of Taipei, 101's foundation is designed to literally pin the building to the deep layer of bedrock below. A 23,000 cubic meter concrete slab sits on top of a complex system of 382 reinforced concrete piles. These piles transfer the building's weight and structure deep into the bedrock, meaning 101 is more than just resting on the earth. It's fused to it. This unique foundation, combined with 101's mega frame and damper, give the building an extraordinary earthquake safety rating that exceeds even that of Taiwan's nuclear power plants.
Inside the 101, during earthquake, you wash out the falling articles. Okay. rather than worry about the falling of the building.
Taipei 101 will not just be one of the strongest and most stable buildings in Taiwan, but one of the strongest and most stable buildings in the world. Building on the main megastructure begins in September 1999.
If I look back, I feel it was more difficult than I expected. But I didn't feel that way when I was working, solving the problems every day.
This isn't a construction workforce, it's a construction army. Here at the Kaohsiung China Steel Plant, some of the most high-tech steel manufacturing techniques in the world are being used to build the various elements of 101's groundbreaking megastructure.
The basic idea of this building is so-called double tube structures, which means we using the steel frame to create the outside tube, and then we using the steel frame and the concrete columns to create inner tubes.
The steel used in Taipei 101 needs to be soft enough to weld, hard enough to carry the building's awesome bulk, and pliable or bendy enough not to weaken or break if it's rattled by an earthquake. Each of these requirements demands a different type of steel, a complex chemical cocktail of carbon, alloy, and refined iron. More carbon makes it stronger, but too much and it becomes stiff, brittle, and hard to weld. The Kaohsiung plant develops 5 different kinds of steel for 101, each with a specific flex-to-strength ratio designed to suit its purpose and position in the building. The challenge for manufacturers is to make perfect steel into perfect components for 101 each time, every time, day after day. The integrity of 101's megastructure requires the super columns to act as single units. But joining 30 90-ton box sections into one seamless unit has never been done before. Yet again, 101 will tread new ground. Ordinary welding techniques simply won't cope with the enormity and detail of the task. Every millimeter of every join requires absolute perfection. Teams of 6 welders work simultaneously. The entire girth of each join has to be heated for the welds to bind. The scale of the task is mind-blowing. Each join takes at least 14 hours to complete. That's nearly 2 years welding in the super columns alone. The high-strength steel and advanced welding techniques used in 101 super columns give the building a strong and flexible backbone built to withstand the shock waves of a severe earthquake. But dealing with the building's incredible weight demands an entirely different type of strength, one that steel alone cannot provide.
A building usually has 2 types of force, the tension force and the compression. And we all know steel works better for tension, and the concrete works better for compression.
The awesome weight or compression loading on the world's tallest structure would crush the super columns if they were hollow. But filling them with concrete to the 62nd floor combines the tensile strength of steel and the awesome compression strength of concrete. Making the system even more robust, engineers develop a concrete mix that is 60% stronger than normal. Concrete able to withstand an awesome 10,000 pounds per square inch of compression. The combined benefit of steel and concrete gives 101 the strongest, lightest, and most flexible backbone of any skyscraper on the planet. A backbone that is about to be put to the ultimate test.